Hey everyone, it's Mr. Fransky here. Today we're going to talk about section 2.3 in our Calc book. It's about continuity and the intermediate value theorem. So this is kind of the first theorem that we have, and it opens up some doors to do some pretty cool stuff. So let's take a look at what's going on with continuity. Before we jump in, let's try a little bit of bell work here about asymptotes that we were talking about in the last section. So what I'd like you to do is find the horizontal and vertical asymptotes of this guy and use directional limits to sketch a possible graph. So if you want to try this on your own, you can pause the video, or you can watch along with me and you can do it with me. Let's see what's going on with this function. So we got x plus 2 upstairs. On the bottom, we got 2x cubed plus x squared minus 6x. So right away, that bottom's just begging to be factored. So I'm going to leave the x plus 2 upstairs. On the bottom, if I take out an x, I'm left with x squared plus x minus 6, 2x squared, excuse me. And then if I factor that further on the bottom, I'm guessing one of the factors is probably x plus 2, because that's sitting on top. It's probably a whole. So it looks like we have x plus 2 upstairs, and we have x times, looks like a 2x and an x. And then to make a 6, it could be 3 and 2, or 2 and 3. It's probably one of those. So if I go 2 and 3, I get 6 and 2. That won't work. But 4 and 3, oh, maybe that'll work. So I put a 2 here and a 3 here. So let's see here. If I get a 4x, and a 4x and a 3x. So I want a positive 4x and a negative 3x. So I'm going to leave that positive x in the middle. There we go. Okay, so yes, indeed, the x plus 2's do cancel. So we would have a whole at negative 2. So it looks like we have vertical asymptote at x equals 0, because we have this x hanging out right here. So you put 0 into this, the bottom will be 0, the top will be a number. Remember that number over 0 is what we're looking for vertical asymptotes. And also x equals, it looks like positive 3 halves. Positive 3 halves would make this part 0 and would not make the top 0. So that's part 2, vertical asymptotes. And then we have to sketch a graph, so let's do that. So x equals 0 is one of our vertical asymptotes, and x equals 3 halves, so that'd be somewhere about here. And then we're asked to use directional limits to kind of try to figure out what's going on here. As far as the horizontal asymptote, notice the degree of the bottom is bigger, so as x increases, the bottom's going to increase without bound, the top will as well, but the bottom's going to be increasing faster. So y equals 0 right here. It's going to be our horizontal asymptote. Okay, so now we're going to use our directional limits to figure out what's going on here. The 0 first. So if we plug 0 in here, we want to figure out 0 from the left and 0 from the right. I'll kind of do it over here. So if we approach 0 from the left side, we don't know if we're going up or if we're going down. We have this nice factoring here, so I'm going to leave it like that. We have 1 over x times 2x minus 3. 2x minus 3, there we go. And so if we plug in something slightly left of 0, we're going to have a slightly negative number on the bottom. Times, so 2 times 0 is close to 0. Minus 3 is going to be a negative number again. So that's going to be a positive. Okay, so 0 from the left, we're going up. We're going to positive infinity. If we approach 0 from the right-hand side, we now have a slightly positive number multiplied by 2 times 0, still close to 0. Minus 3, still negative number. So we have 0 from the right, we're approaching negative infinity. So it's going down like that. If we approach 3 halves, 3 halves from the left side. So if we look over here, the x will be positive, right? Because if we're close to 3 halves, that x will be a positive number for sure. The 2x minus 3, if we're slightly less than 3 halves, that means when we multiply by 2, will be slightly less than 3. So we subtract 3, it's going to be a negative. So we're going down over here. So it looks like we might make some kind of a u in here. We might hit a 0, we might not. It looks like there are no zeros of this guy, so no, we're not going to hit any zeros at all. And then on the right side of 3 halves, so we plug in something slightly bigger, we'll have something bigger than 3, minus 3 will be a positive number, so I have 1 over a positive and a positive, so that'd be positive infinity, so it's going up here like that. So my guess is it looks something like this. And like we said before, there'd be a hole at negative 2, so somewhere in here we could put a little hole. That's about what the function would look like. Don't have to be able to sketch it, but I think it's just good for mental practice to be able to do that. All right, let's jump into continuity. So here's the deal with continuity. Basically, the simple pencil test, they call it. I know some teachers call the pencil test the vertical line test, but the pencil test is really used for continuity. So the pencil test is if you can draw a function without lifting your pen or pencil, then it's continuous. So like a cubic, continuous function, right? You just draw it without lifting your pencil ever. So what are some ways some function could not be continuous? Well, what if you had a hole? So same function, but we had a hole right in there. This is a discontinuity. We're going to talk about the types of discontinuities today. We'll do that a little later. Discontinuity. Okay, so that's discontinuity right there at the hole. Other ways, you could have like an asymptote. Okay, we've been talking a lot about those. So if you have a vertical asymptote, that is also a discontinuity. Okay, vertical asymptote wouldn't be continuous. So this pencil test, can you draw it without lifting your pencil? Well, this hole right here you would have to lift for. This asymptote you would definitely have to lift for, right? And some people are like, well, you're drawing up forever though. Well, okay, but you're never going to get to this part of the graph without lifting your pencil. So pencil test is kind of an informal way of doing it. The real way to do it uses limits. So what we say is the function f of x is continuous at the point x equals c if and only if three things have to be true. And really one thing just has to be true, but we break it up into three because it's really easy then to prove that things are not continuous. So if you think about a function at a point c, let's say c is right here. Okay, this is clearly continuous at that point, right? Because we can just draw right through it. But this is true if and only if, first of all, f of c has to exist. So f of c must exist. So if f of c does not exist, then it's not continuous at that point. So that would be like, for example, if you're dealing with square root of x and you're saying, is it continuous at -2? Well, f of -2 doesn't even exist. It's not even a thing. So that would automatically discount it. It's not going to be continuous. The second thing is that the limit as x approaches c of f of x must exist. So a function is continuous if and only if the function exists, the limit exists. There's a third one here, but so something, this takes out jumps, right? If you have a jump discontinuity, definitely not going to be continuous because you have to lift your pencil, right? But if the limit from the left side and the right side are different, that's no good. This also takes out asymptotes, right? Because if you have a vertical asymptote, that limit would not exist. And then the third thing is that those two things have to be equal to each other. So f of c must be equal to the limit as x approaches c of f of x, right? Because it's possible that 1 and 2 are both true, but we have a removable discontinuity, right? It's possible you have a hole and then the function is somewhere else. This basically says the hole must be filled in. It has to be exactly at the point. So the left side and right side limits have to be exactly the same as the actual function value. Okay, so the function value has to be the same as the limits. And I said before, really only one of these has to be true. That last one is really the most important one because if f of c didn't exist, that certainly wouldn't be true. If the limit didn't exist, that also wouldn't be true. So really you only need number 3 to be true, but 1 and 2 make it really easy to say that functions are not continuous at certain points. It's not too bad. All right, so look at this guy. So does this seem continuous to you? So often they'll ask, is it continuous on a closed interval? So from -2 to 2, they might say, is this function continuous? So if you let x go from -2 over here to 2 over here, is the function continuous? Well, between -2 and 2, I think it's pretty clear that it is. And it's weird because it stops. So the question might be, is it continuous at the endpoints? So endpoints are kind of an interesting thing. Can you have continuity at an endpoint? And the answer is yes, you can have continuity at an endpoint. What you do is just instead of using the limit, that last piece just becomes if the limit from the left side or the right side is equal to the function value, then you're going to be okay. So you might not remember, but the equation for a semicircle, remember a circle has the equation x squared plus y squared equals 1, but that's the entire circle, right? If you just want a semicircle, you can solve this for y. So you would have y equals the square root of 1 minus x squared. And it could be plus or minus, right? That would get you the bottom half of the circle as well. The negative part is the bottom half of the circle. The positive part of this is the top half of the circle. But in this case, we're only concerned about the top part, so I'm just going to get rid of that. So it's just the positive part that we have right here. So what we're going to do is we're going to do the limit as x approaches. Let's look at -2 first. -2 from the right side, right? Because we're approaching it from the right. Here, there's nothing on the left of the square root of 1 minus x squared. Except it's not 1. 1 is, so this would be r squared. In this case, r is 2, so that should actually be 4. That should be 4 there and a 4 there. There we go. Now we just plug 2 in here. Plug 2 in here. 4 minus 4 is 0. So this is equal to 0. So that is equal to the function value, right? Because we just got to plugging it in. So we are continuous at -2 for sure. And then over here on the right, if we do the square root of 4 minus 2 squared, that is equal to 0, which is equal to f of 2. Okay, so we're good over there as well. So yes, this is continuous from -2 to 2, including the endpoints. Cool. All right, so Sometimes you get problems like this where they're looking for whether a function is continuous at a point. And we're actually going to take a look at this guy in terms of limits as well. Looks like my limits kind of got faded out there. So the limit, let's see, x approaches 0 from the right side, because that's the only spot where it's approaching there. And then for 1, we'll have to do the limit as x approaches 1. All right, so f of 0, what's f of 0? Well, if we look at f of 0 right here, it looks like it's 2. If we look at 1, f of 1 looks like it is 1. Okay? So as we approach 0 from the right side here, those y values, as we march up the line here, are getting closer and closer to 2. So the limit as x approaches 0 from the right of f of x is equal to 2, which is the same as the function value. So we are continuous at 0. Okay? Now for 1, f of 1 is 1. The limit as x approaches 1 of f of x from the left and the right sides. The y values are getting closer and closer to 1 from both sides. So yes, we are continuous at 1. Cool. So now we're going to take a look at this with some different values. So how about at 2? What is f of 2? Well, that solid dot is up here at 1. But as we approach 2 from the left and right, what's going on? That looks like a limit does not exist situation. So this is not continuous at 2. And you could have told me that just by looking and said, well, you have to lift up your pencil there. But we're not continuous at 2 because of the definition. The limit is not the same as the function value. At 3, 3 is right here. F of 3 is 2. As we approach 3 from the left or the right, even though we have a corner here, some of you might already be thinking about like the slopes. Not concerned about that now, just concerned about the continuity. So as you approach 3 from the left and the right, those function values are approaching 2. So we are continuous at 3. F of 4, so f of 4 is actually up here at 2. But as we approach 4 from the left side, what do those y values appear to be approaching? Looks like they're going to 0. So we are not continuous at x equals 4. That's what all there is to doing continuity. If you have a graph, super easy, right? Story of our lives so far. If you have a graph, it's really easy. We'll take a look at some later that are different than graphs, where we have to do some algebra on them. So let's take a look at what's going on with different types of discontinuities. So I'm actually going to make a tree map here. Miss Rail taught me how to make tree maps. So let's take a look. So first we kind of have one that's kind of all by itself over here. Those are the removable discontinuities. So a removable discontinuity is one that's a hole. And it's possible it's filled in somewhere else. I'll kind of put parentheses around this. It's possible it's filled in somewhere else. It's possible it's not. But where does this fall short? The limit exists, but the problem is the function value, f of c, if c was right here, whoops, is not equal to the limit as x approaches c of f of x. Right? That's your issue, is that the function value is way up here. That's f of c. But down here, this is your limit as you're approaching c from the left and right. So then we have the 3 types of non-removable discontinuities. So there are 3 types here if you want to make room in your notes. 1, 2, and 3. So the first one is the jump. Okay, jump discontinuity is like it sounds. The step function is a really good example. Every integer, you've got a discontinuity. It's a jump. Okay, it could also just be something like this, right? I guess that have to be an open circle. Okay, so jump discontinuity is where you change value. The next one is infinite. Infinite discontinuity, just when you hear that, think about an asymptote. So asymptotes are different than jumps, because jumps just stop and immediately go somewhere else. Infinite discontinuities, you're getting really close to a vertical line, but you never quite get there, and then it stops. Or it doesn't stop, it jumps to a different value. The last one are called oscillating. These are kind of weird discontinuities. If you start exploring these graphs like on Desmos, really weird stuff happens. But oscillating discontinuities always happen with trig functions. And usually it's stuff like sine of 1 over x or cosine of 1 over x. As you get really close to 0, this never isn't defined except for at 0 itself. But the weird thing is it oscillates faster and faster and faster. So if you graph this, it's always going to be sandwiched between -1 and 1. We know that. But what's going to happen is it kind of starts out mellow. And then what happens is it starts to oscillate really fast towards the middle. And it actually oscillates an infinite number of times in any interval that you have around 0. So it does really weird stuff at 0. And it's not a jump, because as you get close to 0, it's not like it just jumps position. It oscillates faster and faster and faster and infinitely fast when it gets close in. If you take a look at this part on Desmos, it's really weird. Take a look at sine of 1 over x. So this is just, it doesn't fit any of the other categories, so it has its own category. That's basically what's going on there. All right, so let's take a look at some different functions and figure out what kind of discontinuity they have. If you want to try these on your own, feel free to pause the video. Otherwise, maybe you want to watch one of them, and then you could pause and try the others. But let's just kind of take a look at what's going on here. So this first one looks like it wants to be factored. So I'm going to factor the top, x minus 2x plus 2. So there's nothing that cancels, right? Nothing cancels out. But we will have an issue at x equals 3. At x equals 3, on the top, we would have 9 minus 4, which is 5. So we'd have 5 over 0. That's a number over 0. This is a vertical asymptote. That is an infinite discontinuity. So we have an infinite discontinuity at x equals 3. Remember, things happen at x values, right? Often we're interested in the y value if we're asked for the value of the function, but things happen at x values. X is like your roadmap. It's like, where along the x-axis does it happen? And then you can talk about the value if you need to later. The next one, piecewise functions are like telltale signs of possible jump discontinuities, but we have to check it out and see what's going on. So we have x squared minus 1 when we're less than 0. Remember, x squared is just a parabola, kind of like that shape. And we're moved down 1, and it's strictly less than, so we're getting an open circle here, and then it'll kind of curve up like that. And we got 2x if x is greater than or equal to 0. So we get a solid dot at 0, and then a slope of positive 2 like that. That definitely looks like a jump at x equals 0. And that's our discontinuity there. Next up, once again, looks like we should factor. So x and x. And I think I may have written this one down wrong. I think this is supposed to be a 2. I'm going to say it's a 2. Let's see what happens. Looks like x plus 3, x minus 2 over x minus 2. Those x minus 2's will cancel. So we have a removable or a whole. Removable. Sorry about that mistake there. At x equals 2. So if you were to graph this, it would look like x plus 3, 1, 2, 3. And then at 2, we'd have a whole. That's what this would look like. Next up, sine 1 over x. We already talked about this one. It's really hard to come up with a different example for this because there are so few that do anything like this. But this is going to be an oscillating discontinuity. Cool. At x equals 0. Right? Because 0 is the only place this has an issue. Anything else, you could just plug it in and you'd have a continuous function. All right. So that's kind of what's going on with discontinuities. Intermediate value theorem. So first thing we're going to talk about with the intermediate value theorem is just kind of why it's related to continuity and also kind of what the heart of the intermediate value theorem is. So the idea here is that if you have an x equals a and an x equals b, and we have right here mapped up to f of a, so this is some kind of a function that maps up to its function value there. Let's say right here is f of b. So the idea is if the function is continuous, that means to get from here to here, you must be able to connect them with a smooth line of some sort. It could go way up or way down, but it's got to connect these two without ever breaking. So what that means is you've got to cover, usually it's kind of something simple like that, but it's got to cover every y value between f of a and f of b. Again, it could go outside. You might have something like this, right? It could go outside and come back, but still, if you made a horizontal line anywhere between f of a and f of b, it's going to hit the function somewhere, right? This is as long as the function is continuous, okay? Now, why is this useful? Well, if you have an a that gives you a function value below 0 and a b that gives you a function value above 0, you're guaranteed to cross through 0 sometime. So it's kind of nice to find zeros. So if like f of a is less than 0 and f of b is greater than 0, then there has to be some point in the middle. There has to be some, let's call it c. So there is some c where f of c has got to be equal to 0. So a little bit more formal definition of this. If f of is continuous on AB, so from A to B here, then it takes on every value between f of a and f of b. Now again, it can go outside, right? This actually goes on some values outside, but every single value between f of a and f of b must be hit by the function at some point. Now, why is it important for it to be continuous? Well, if the graph isn't continuous, right? If we have like a removable discontinuity here, then there's one spot that doesn't get hit. Okay, so it absolutely must be that f of x is continuous. On the AP test, you have to, they sometimes will say like justify your answer. All you have to say is f is continuous. If you forget to say that f is continuous, then you don't get the points. You don't have to even mention intermediate value theorem. Oftentimes people say like by IVT, but you must say since the function is continuous. Okay, so it's kind of like an AP Stats. If you take an AP Stats, you have to like justify using certain steps. You have to like give evidence for your answers. And often that means like proving that n is greater than 30, or that you know, you have a simple random sample, right? It only works if it's a simple random sample. You have to state those things. Same thing here. All you have to do is state that it's continuous. If a function is continuous, then it must hit every value between f of a and f of b. So how is this useful? Oh, I got a cross out on this one because it's not continuous. All right. So how is this useful? On which interval must x cubed plus x plus 1 equals 0 have a solution? So what we're looking for here, we're looking for an x value, any x value, that gives us a number above and below, or below and above. If we can prove that, when we plug it into the function, if we can prove that it's one is above and one is below, that guarantees, because all polynomials are continuous, that it's going to cross through somewhere. That's worth writing down. All polynomials are continuous. So if you're ever given some kind of a polynomial, you know it's going to be a continuous function, because all polynomials can be drawn without lifting your pencil. So let's check this. Let's just check these. So we plug in -5. -5 cubed is -125. And then we'll have -5, and then +1. That's a very negative number, right? That's -129. You plug in -3, you get -27. -3 plus 1. That's also a negative number. Okay, so we have two negative numbers. That doesn't help us, right? So from -5 to -3 would have two negatives, not guaranteed to go through 0. It could, but the intermediate value theorem doesn't guarantee it. So -3 gave us what? -29. If you plug in -1, you get -1 minus 1 is -2, plus 1 still negative. Okay, so that one's no good. A was no good, B was no good. If you try C, plug in -1, that gives us a negative number. You plug in 0, ooh, that gives us a positive number. So -1 and 0. At -1, we get, what do we say, -1? And at 0, we get +1. So somewhere between -1 and 0, we must go through the x-axis. It has to touch 0. Yeah. Okay, so we have covered everything that needs to be covered. I do have some more examples here. Usually we do this over 2 days. But I have it prepared just to keep going with the examples. So if you'd like to watch these examples, you can. If you maybe want to try the homework and then come back and watch these, if you get stuck, you can do that. But basically, I'm going to do some discontinuities, and then I'm going to do another piecewise function asking about continuity. And then I'm going to take a look at a intermediate value theorem problem, similar to the last one we just did. So feel free to follow along with me if you'd like to. So this first one, we're just talking about which discontinuity type do we have. Absolute value is really good at making jumps. Oftentimes when you have absolute value, like something will happen like this, and then it'll be a mirror image on the other side and keep going, something like that. So really good for making jumps. But we also might have some vertical asymptotes on the bottom. So let's see if we can factor this. We have absolute 2x plus 1. On the bottom, 2x and x. And then -3. So we have to have a 3 and a 1. 6 and 1 seems like it will work. 6 and 1 would make a 5, but also a 3 and a 2 would make a 5. So let's see if this is going to work out. So -3 has to have a positive and a negative. So we subtract 6 and add 1. Yep, that'll work. Okay, so actually 2x plus 1, look at that. They cancel. That's interesting. Okay, so it looks like we have some kind of a removable discontinuity at maybe -1/2. So x equals -1/2. We're thinking we might have removable. It also might be a jump, so we'll have to take a look at that. And then at x equals 3, it's definitely a vertical asymptote, so that's an infinite discontinuity. Now let's see what's going on at -1/2. Usually when things cancel like this, it's removable, but I'm going to kind of put a question mark there because I'm not sure yet. Let's try approaching it from the left side. So we approach -1/2 from the left side. -1/2 from the left side, the top is always positive. It'll be very close to 0 on the top, but it'll be a positive number. On the bottom, this will also be very close to 0. We're approaching it from the left. That means this number will be slightly less than -1. You add 1 to it, it's still going to be negative. The weird thing about this, though, is these two values are exactly the same, so they will always cancel, but it's going to give you that little negative there. Negative 1/2 minus 3 is going to give you another negative. So we have two negatives on the bottom. That'll give us a positive value of, those will cancel, so you'll have 1 over negative 1/2 minus 3. It's going to be positive, though. Okay, if we approach from the right, side, top is now positive, bottom is positive. That x minus 3, though, is still going to be negative, so that'll be a negative value. So this is actually not a removable, it's a jump. If you don't believe me, throw that into Desmos, and you'll see that at negative 1/2, it's going to do like kind of a change, kind of like this. Absolute value is really good at making jumps happen. All right, let's take a look at B. We got a piecewise function. Definitely thinking that's going to be a jump discontinuity, but let's see. They might actually connect. So we got x squared plus 1 for x greater than or equal to 2. So here's 2. We plug in 2 in there, we get 5, and that's going to be a solid dot. It's going to be going up like that. X less than 2, we have negative x plus 7. 1, 2, 3, 4, 5, 6, 7. Yeah, so that's going to be like coming down like this. Where are we going to intersect? Negative 2 and 7 are 5. Actually, they do connect. Look at that. Okay, you plug 2 in here, you get 5. You plug 2 in here, you get 5. So this is actually a continuous function. And sometimes that happens. Sometimes it works out where they link up, and you could draw it without lifting your pencil. That's it. Here we got a four-way piecewise function. X over 2 is a line. So we're doing that until negative 3. And we actually go through negative 3. It really happens until 2. But at negative 3, so we got x over 2 is like this. And we keep going until we get to 2. And then we have a solid dot. But at negative 3, the actual function value is 0. So we have a hole there. Okay, so we have a removable discontinuity at x equals negative 3. At 2, let's see what happens when we plug in here, 2. 2 plugged in here is 0. It's going to be an open circle. It's this is a parabola shifted right 2 that's going downwards. It's going to be something like that. So then we have a jump at x equals 2. So removable at x equals negative 3. Jump at x equals 2. Nice. All right, so continuous at a bunch of different points here. This is our piecewise function. So at x equals negative 3. 1, 2, 3. Nope, it's a jump. Jump discontinuity, so no. Remember, we're checking the left side and right side limits and seeing if they're the same. From the left side, we're approaching 0. From the right side, we're approaching 1. Not the same. At negative 2, yeah, that's fine. From the left and from the right, both values are approaching 2, and that is the function value. So yes, continuous at 2. At 0, we have a jump, so that's a no. From the left side, we're approaching 0. From the right side, we're approaching negative 2. At x equals 1, yeah, that's a continuous part of the function, sure. You can draw right through it without lifting your pencil. At 2, this is kind of weird. We have an infinite discontinuity, but there's like a dot in the middle. I would still call this infinite because it's an asymptote. It looks like this would be like a piecewise function where they just say, and by the way, at 2, the function value is 0. At 3, once again, we're back to our continuous function land, so yes, it's continuous at 3. Left and right side limits are the same, and they're equal to the function value. Cool. Find any interval you want where x squared minus 2x equals 6 has a solution. So I can think of a couple ways to do this. It's definitely going to be intermediate value theorem. Anytime you have to prove that some kind of a solution exists, it's going to be intermediate value theorem, or later on we'll learn mean value theorem, which is a similar idea as well. What I'm going to do here is I'm just going to check some numbers and find one that's below 6 and one that's above 6. Okay, so I'm going to kind of think about this graphically. So if I plug in 0, I get 0 minus 0, which is 0. So 0, 0. I'm trying to hit 6. So now what I have to do is I have to find a value that gives me a value above 6. Well, a big number would work. How about like 10? 10 squared is 100 minus 20, sure. At 10, I'm going to be up here at 80. And we said all polynomials are continuous, so for somewhere in between here, because this function is continuous, so f of x equals 6 between 0 and 10. You might be able to find a tighter interval, but 0 and 10 works fine, right? At 0, we're at 0. At 10, we're at 80. Somewhere in between there, it's for sure got to hit 6. This clearly is not to scale, right? 6 is not almost halfway to 80. All right, I believe that's all I have for you guys. Yeah, so make sure you try the homework. There's a packet on continuity if you want to try that. We got lots of limit worksheets you could be working on. Otherwise, that's it. I love you guys. That's why I'm here. Have an excellent day.